Okay, let's go ahead and get started. So last class we had a more general discussion of the Poincare group, the Lorentz group, and the representations thereof. And we made the general statement that to some extent a particle can be defined as an irreducible representation of the Poincare group. And we classified these irreducible representations, and we showed that they are essentially given by pairs of representations of SU2. So what I'd like to do now is just review that basic setup for you for a few minutes, and then use that dictionary to start constructing more interesting sorts of field theories that describe particles with spin. Okay. So just to summarize our conclusion of last class, so a particle with spin j, which is going to be some half integer, is described not by a single field, but rather by a collection or multiplet of fields that we could schematically denote phi sub a, where a is an index that will label the different fields in this multiplet. And these fields depend on your position in space-time as usual. And the point is that these will transform under the Lorentz transformations in some more complicated way than the simple scalar field. So in particular, if you have a Lorentz transformation that's characterized by a 4x4 matrix, which we showed on an earlier problem set, can be thought of as the exponential of an anti-symmetric matrix omega. I believe I called that delta omega actually last time rather than omega. So that if we were to expand for small delta omega, then an infinitesimal Lorentz transformation would be described by a 4x4 matrix that's given by the identity matrix, plus this anti-symmetric matrix, delta omega mu nu, plus higher order terms that we typically neglect when we're studying the algebra of infinitesimal Lorentz transformations. And under such a Lorentz transformation, the fields phi a are operators which transform as operators always do under a symmetry in quantum mechanics. That is to say, by conjugation by some unitary operator associated with the Lorentz transformation. And for a particle with spin, that action of the Lorentz transformation really acts on the field in two distinct ways. So the first way it acts on the field is just by moving the point in space-time. Okay. So the point x mu goes to a new point, lambda mu nu x nu, which I've abbreviated lambda dot x just to prevent an explosion of indices. But in addition, we have a matrix L that appears here, which describes how the indices that label these fields in the multiplet transform among one another as one undergoes a Lorentz transformation. And the point, as we discussed last time, is that these matrices L have to form a representation of the Lorentz group. So in particular, the action of matrix multiplication has to be the same, has to obey the same group multiplication law as the composition of Lorentz transformations. Okay. And so in particular, what we're going to do today is we're going to work this out for some simple representations of the Lorentz group, and we'll work out explicitly what these matrices L are and how we can use these fields to build up interesting sorts of equations of motion, action, interactions, and so forth. Okay. So very often in our discussion today and moving forward, I'm going to be a little bit relaxed, and I'm actually going to just omit the dependence on x. So sometimes I'll just omit that x there and that lambda.x there, so that the only thing that I'll really be writing down, which is the only sort of new ingredient, is the behavior of these matrices LAB. Okay. So typically, we will study infinitesimal Lorentz transformations. So this is sometimes referred to as the Lie algebra, or algebra of Lorentz transformations. So in this case, we can, for example, take this unitary matrix and expand it to first order in the parameter delta omega, which will be taken to be very small if we have an infinitesimal Lorentz transformation. And the linear terms in this expansion are some Hermitian operators that I've called M mu nu, which are the generators of the Lorentz transformation. So the generators of the Lorentz transformation in the representation that describes these fields phi. Okay. And similarly, we can take these matrices LAB and expand them, and at linear order there will be some coefficients which will be given by S mu nu, which will be some matrices. Okay. So S mu nu is really something with 4 index. It has a space-time mu and nu index, and an upper and lower A and B index that tells you how it's acting on the various fields in this multiplet. And so if we only consider an infinitesimal Lorentz transformation, then you can just take this expression here and expand to linear order in M here. And at linear order, phi goes to phi plus delta phi, where delta phi is essentially given by the commutator of phi I with these generators M. So this is the usual sort of expression, say in quantum mechanics, that the variation of the field is under some sort of symmetry, is the commutator of the, so the variation of some operator under some symmetry is the commutator of that operator with the generator of the symmetry. Okay. So for example, this is the Hamiltonian equation of motion that says that in the Heisenberg picture, the time derivative of some observable is the commutator of that observable with the Hamiltonian. So this is just a slightly different version of that statement. And this commutator really reflects how the field transforms in 2 different ways. So first of all, there is the transformation of the field just due to the fact that the space-time point is changing. Okay. So here that's given by what I called last time L mu nu acting on phi A. L mu nu is x mu d nu minus x nu d mu. And then, so that just reflects how the point in space-time changes under a Lorentz transformation. And then we have the sort of more interesting and new piece that reflects the fact that these indices are mixing with one another under a Lorentz transformation. Okay. So this is all just sort of a lightning summary of what we discussed last time. I realize there's a lot of indices flying around everywhere. Maybe I should pause here and just make sure that everything is clear. Okay. So this is all a bit abstract, and in the next several minutes I'm going to make this much more explicit, working out the example of spinor fields, which are the simplest sort of non-trivial representations of the Lorentz group for certain definitions of simple. But let me, before I do that, pause and see if there are any questions. Okay, no questions. Good. Okay. So last time, we saw that the representation theory of the Lorentz group reduces to that of the rotation group SU2. So how did that work? Well, if you think about these generators M mu nu of the set of rotations, then the M mu nu are the set of Lorentz transformations, then those Lorentz transformations that just mix spatial indices are nothing more or nothing less than the rotations. And those that mix a time index with a space index are the boosts. And there are three rotations generated by the usual rotation operators, Ji, along with three boosts that are generated by some vector k, where ki describes the boost that mix the time component t with the xi direction. And so, for example, you could verify, given this expression here for the generators of the Lorentz transformation, that indeed, say, what I called script L12 is really the rotation about the z-axis, the x3 axis. X1 d by dx2 minus x2 d by dx1. And we saw that the algebra of the infinitesimal Lorentz transformations takes a very simple form when you write it in terms of this special set of complex combinations of the rotations and boosts. Okay. So in particular, what you have is that the commutator of Ni with Nj is given by the usual formula for the generators of SU2. Sorry, that's an epsilon symbol. Sorry if you can't, that wasn't written very clearly. And likewise for the N daggers. Okay, so I, epsilon, I, j, k, n, k, dagger. And the ni's and the ni daggers commute with one another. Okay. So what this means is that the algebra of Lorentz transformations really splits into two SU2s. Okay. And we typically give a name to these. We usually call these SU2 right and SU2 left, which we'll denote by indices R and L there. The only subtlety, and this is something that will come back to haunt us later on in this class, is that the N's are no longer Hermitian operators. Okay? The M's were Hermitian operators, J and K. At least the action originally was phrased in terms of Hermitian operators. But the N's are no longer Hermitian operators. That's something that we'll have to return to and think about. Okay. Yes?
The way you write now, there is a direct interpretation for the N's.
The interpretation of an N? What is an N? An N is, so J generates an infinitesimal rotation. K generates an infinitesimal boost. N generates an infinitesimal combination of rotation and boost. Simultaneous rotation and boost. Okay. With a funny factor of I. Okay, that's life. Sometimes in life you have or at least in physics, if not in life, you have factors of I. Okay. Good. Yeah. So Yeah, I mean, if you want to think about it, rotations are something you hopefully understand reasonably well. And you can think of the ends as the complex generalization of rotations that you need to do in order to incorporate boosts into rotations. Okay. And so we'll see that given this way of thinking about the Lorentz group, actually you can just recycle all of your knowledge about about SU2 and particles with spin and in non-relativistic quantum mechanics to understand relativistic quantum mechanics. Good. Yes?
What if we apply this answer formula? Would that make any difference?
Well, okay. The problem is that because of this factor of I, so remember what we're looking for is we're looking for representations in terms of some matrices acting on these L matrices acting on an algebra, a multiplet of fields. Because of this factor of I, you can't really interpret it as acting directly on the space-time itself. Okay. I mean, it's sort of this is sort of an important point that we'll get back to, which is that, the representations of the group can sometimes allow for more generous structures than are originally obvious in terms of the space-time. Like, this is why spinors are sort of confusing, right? Is that, a vector is something that arises when you think about points in space-time and differences between points. A spinor is not really something that arises in this way. It's something that only arises when you think about the possible unitary operators that can realize the symmetry acting on a Hilbert space of quantum mechanics. Okay. So it's kind of a fundamentally quantum mechanical object. Yeah. So you can't really think about these ends as acting on space-time. I mean, you sort of can, but you have to be, they're funny factors of I that appear if you do that. So I wouldn't want to take that too seriously, because then you would have to complexify space-time. And sure, you can complexify space-time. We do it all the time, but let's not do that right now. Yeah. Right. Okay. I could go on a digression about that, but I'm not going to. Good. Let's just say that if you wanted to think about these as real symmetries acting on a complexified space-time, you certainly could. So previously when we discussed, see here I am going on a digression. So previously when we discussed, for example, how you define the vacuum state by doing a little complex rotation in the complex time plane, we imagined taking t to it. If you took t, so remember ki looks like tx minus d by dt, x d by dt. Okay. So if you took t to it, k would go to ik, and that would be precisely this factor of I here. So it is literally the case that if you went to Euclidean space, a four-dimensional Euclidean space by taking t to it, then these SU2s would be literal rotations of that space. Okay. So in particular, if you took t to it, then the invariant interval would be the usual Pythagorean, line element invariant interval of four-dimensional Euclidean space, whose symmetry group would be SO4, which is the rotation group of a three-dimensional sphere. And it is literally the case that SO4 is SU2 times SU2. Okay. That those are the geometric rotations of that space. Okay. So that funny factor of I, though, means that you can't really make that interpretation when you think about Lorentzian signature. Okay, end of diatribe. Diagram. Okay, good. Okay, so how do we construct spinors? Okay. So the representations are then labeled by a pair of integers. So remember that there's a representation of SU2 for every integer n. If you don't remember that, it's problem 3 on the problem set that's due on Friday. So the simplest representation, of course, is the representation where all of the matrices Ji are just equal to 0. Okay. So for example, the spin 0 representation, or otherwise known as the one-dimensional representation, is the one where all of the ji's are just equal to 0. Okay? That's obviously a representation because the commutator of 0 with 0 is epsilon I jk times 0. Okay? So that obeys the usual SU2 algebra. The spin 1/2 representation, otherwise known as the 2, because it's a two-dimensional representation, is the one where the ji's are given by the Pauli matrices, okay, 2 by 2 matrices, Hermitian matrices which obey the rotation algebra, namely that the commutator of sigma I with sigma j is epsilon I jk times sigma k, okay, with an I here. And there's a conventional factor of 2 here. And then there are, of course, higher dimensional representations, okay, which you may or may not work out on your problem set this week. I don't actually remember if I assigned that problem. Okay. So the simplest representation which will be the left-handed spinor representation, is the representation where all of the n's live in the two-dimensional representation and the n daggers live in the one-dimensional representation. Okay. So that means that all of the ni's live in the two-dimensional representation and the ni daggers live in the one-dimensional representation. And the field, which I called phi A up above, will be a two-component object. So I'll call it psi, which is the typical symbol that we use to denote particles with spin. And it has an index A that takes two possible values. And all we now need to do in order to specify the transformation properties under the Lorentz group is work out explicitly what these matrices that I called S are up here. Yes?
How do we know that A is 1 or 2?
Well, it,
Double.
what's that? Well, let's put it this way. It has to have two indices on which, you know, this, the first SU2 is going to act, and it has to have one index on which the second SU2 acts, and 2 times 1 is equal to 2. Okay. So that's the logic. Let me write out explicitly how it acts, and then I think everything will become a little bit more clear. Okay. So in particular, the matrix S mu nu is then given by the statement that Ni is equal to sigma I and Ni dagger is equal to 0. Okay. So in particular, Sij in the left-handed spinor representation, so I'll put a little L to denote that, is given by 1/2 epsilon ijk sigma k, and S0I is given by 1/2 I times sigma I. Okay. So why is this? Well, remember that so n is equal to j plus ik. So j is equal to n plus n dagger. And dagger is equal to 0. N is equal to sigma. So this is just equal to sigma I. And then j itself was just one of the rotation matrices. So in terms of the Lorentz generators, it's 1/2 epsilon I jk s jk. Okay. And so that just leads to this first equation up here. And then similarly, ki is going to be, well, n is j plus ik, so k is minus I times ni minus ni dagger. So that's minus I times sigma I. And that is supposed to be I, oh, I'm sorry, I guess, minus I times m0I. So, no, sorry, that's supposed to be m0I. Okay. And of course, as usual, I forgot my factors of 1/2 here, because there's a factor of 1/2 here, which leads to these factors of 1/2 here. Okay. And I may have made a sign mistake. Let's see, did I make a sign mistake somewhere? Okay. Well, in any case, you know, it really depends on which one you call n and which one you call n dagger. Okay, good. So this is the defining property of the left-handed spinor representation. And so just to be completely explicit, under a Lorentz transformation, how does this spinor transform? So typically we characterize a Lorentz transformation by a set of 6 numbers given by this antisymmetric matrix, delta omega. So if you want to describe that Lorentz transformation a little bit more physically, remember a Lorentz transformation is just a rotation along with a boost. And so we could write delta omega ij as epsilon ij k theta k for some set of 3 numbers theta k, and delta omega 0I as beta I. Then physically, this would describe a Lorentz transformation by a set of angles. So describing a rotation by some set of angles theta I about the xi axes, and a set of 3 boosts, beta I, which mix the time and the xi direction. And under such a Lorentz transformation, the variation of one of these spinors is just given by this matrix here. So it's given by 1/2, just plugging in that first term, I theta I minus beta I times sigma I acting on psi. So under a rotation by an angle theta, psi goes to I theta sigma I times psi. Okay. That is exactly how a spin 1/2 particle in quantum mechanics transforms under a rotation. And under a boost by a parameter beta in the xi direction, the left-handed spinor just goes to psi plus beta times sigma without the factor of I. Okay. So you can see that, you know, we've used, so the transformation property of spinors in special relativity is very similar to the transformation properties of spinors in quantum mechanics. Okay. The only difference being that between a boost and a rotation is the lack of this factor of I here. Okay. Good. Okay. So these are the left-handed spinors. So I'll typically denote them with a little subscript L here. L is not an index that labels the two states. Usually, if we can help it, we don't want to write that index out explicitly. So L instead just labels the fact that this is a left-handed spinner, transforming the 2-1 as opposed to the 1-2. Okay. Now, the expression that I've written here for the transformation property of our left-handed spinner is sufficiently simple that you can actually understand how a spinner will transform under a finite representation rather than just an infinitesimal one. A finite Lorentz transformation rather than an infinitesimal one. In particular, under a finite Lorentz transformation, psi will go to e to the 1/2 I theta I minus beta I times sigma I acting on psi. Okay. Where all I've done is I've exponentiated this factor here. And so this is sort of the completely explicit representation for how this spinner transforms under a Lorentz transformation. And so what we're going to do next is we're going to look in more detail at this spinner transformation rule and use this to construct various sorts of scalars and vectors that we can use to build up equations of motion. Now, I appreciate that if you haven't dealt very much with spinners before, this can all seem a little bit foreign, but it's just a language that you're going to get used to eventually. And so at this point, this should all be quite similar to the sorts of spinners that you've dealt with in your quantum mechanics class. So when you describe a spin 1/2 particle in quantum mechanics, it's a two-state Hilbert space. It's a two-component vector. The rotation generators are given by 1/2 times the Pauli matrices, and exactly the same thing is happening here. The only difference being that we had to take we can also incorporate boosts, and the way that boosts act is almost exactly the same as the way that rotations act, except without that funny factor of I. Maybe I should pause here and see if there are any questions. I mean, this is pretty darn important, so feel free to ask questions. Was that more or less clear, that derivation? More or less? Yes? Yes, so yeah, I mean, so as I mentioned earlier, I'm being a little sloppy in that I'm not writing out explicitly the transformation of the point itself. I'm only writing out how the index transforms. Okay. Yes. That's correct. That's correct. So, for example, if you want, yeah, no, that's a very good point. So you would really want to write something like, theta I times, I don't know what did we call it? I don't know if I gave a name to this guy, but yeah, you would write it as theta I times epsilon I j k xj d by dxk plus beta I times t d by dxi minus xi d by dxt. Okay, you would write something like this, acting on psi. Okay. But I'm going to be a little, just to keep life simple, I'm going to really, just try not to bother writing this down as much as I can, because all of that stuff is exactly like how it is for a scalar field. Absolutely, the parameters are the same. There's one Lorentz transformation which acts both on the point and on the indices. Okay. Good point. Yeah. I mean, it's important that, in quantum mechanics, you will often talk about a particle with spin that has at a fixed location in space, and so you won't talk about its spatial. You often don't talk about a particle that is a wave function and has a spin 1/2 index. I mean, you could, but you don't often tend to do that in quantum mechanics. But that's certainly what we're doing here. It has both a space-time position and an index. I mean, it's an interesting actual fact. You could try and ask whether there are representations of the Poincare group that are finite dimensional, and so that they don't have a dependent, because all of your fields depend on a point in space, you really have infinite dimensional representations of the Poincare group. You could ask whether there are any finite dimensional representations. And the answer is that it turns out that there are none. Okay? At least no unitary finite dimensional representations. And so that's sort of a proof that a particle has to be some sort of localized excitation associated with each point in space-time. Yes?
Given that n dagger is adjoint with n,
Yes.
naively I would think that the representations they transform under need to be related by something nice like
Okay, right. So, no, I mean, that's a great point. So, I mean, the important point here is that, I theta times sigma I is the transformation rule that you would expect for some nice Hermitian operator. Okay? Whereas you don't have, because you're missing this factor of I here, there's something a little different about the way that these states transform under boosts. And so that means that when we try and, at the end of the day, write down scalars from which you would want to construct an action, okay, to describe the dynamics of your theory, that means that we're actually going to have a very hard time doing that, okay, without mixing psi left and psi right in some interesting way. Okay. So yes, no, that's an important point. That's a very important point. Okay. We'll get back to that a little later in this class. Good. Another question? Okay. Let me maybe make one important point from this formula. And this is something that you've already seen in quantum mechanics, but it's worth reiterating, which is that let's consider the case where you have just a rotation, say, about one axis by an angle 2 pi. Okay. Then the matrix that you get is e to the pi I theta times one of the Pauli matrices. Okay. Could be sigma 3, it could be sigma 1, it actually doesn't matter. The point being that this is minus 1. All of the Pauli matrices are square roots of unity. Okay. So that means that under a 2 pi rotation, psi goes to minus psi. Okay. Now under a 2 pi rotation, the space-time point comes back to itself. So this literally means that you take a spinner, you rotate it by 2 pi, it doesn't come back to itself, it comes back to itself up to a minus sign. Okay, pretty funny, right? This is exactly the same thing that happens in quantum mechanics, and it's just as true in quantum field theory. Now, technically speaking, this actually means that what we're considering are not exactly representations of the Lorentz group, but rather what are known as projective representations of the Lorentz group. So remember, a representation is a set of matrices. So in particular, we're interested in unitary matrices that obey the group multiplication law. Now, if your matrices all obeyed the group multiplication law, then if, two matrices, their product is equal to 1, then the product of those unitary, if lambda 1 times lambda 2 were equal to the identity, then u of lambda 1 times u of lambda 2 would have to be equal to the identity. But we've seen here that if you do a rotation by pi and a rotation by another pi, you don't get the identity, you get -1. So that means that what we're actually considering here are not what a mathematician would call a true representation, but what's known as a projective representation, where you're allowed to put a little phase there. And the important point is that in quantum mechanics, you're required to allow, you're always allowed to put a phase there. Why are you allowed to put a phase there? In quantum mechanics, phases are in wave functions are unobservable. Similarly, for the field side that we're considering here, the phase, the -1 that appears out front, is unobservable. So, in fact, it turns out the fact that the Lorentz group and the rotation group SO3 allow for these projective representations is related actually intimately to the topology of these groups. I don't necessarily want to get into a detailed discussion of the topology of these groups, but the topology of these groups is also closely related to the relationship between spin and statistics. So in particular, it turns out to be a true fact of nature that all particles with even spin are bosons and all particles with odd spin, half-integer spin, are fermions. That's not something that is going to be obvious from anything that I've said so far or anything that I'm probably going to say this semester, but it's a true fact, and the proof of it is related to really the topology of these symmetry groups that are appearing here. Okay, so that was all just a bit of an aside. So just as there are left-handed spinners, where one of the SU2s is a two-dimensional representation and the other is a one-dimensional representation, there are also right-handed spinners so I'll call them psi right, and they differ from the left-handed spinners only in the sign of beta I in the transformation rule for the right-handed spinner. Now, how could you see that? Well, remember that the two different SU2s, one was J plus IK, the other was J minus IK. So they're related by flipping the sign of K. K is the generator of boosts, and so that corresponds to flipping the sign of beta here. So that under an infinitesimal Lorentz transformation, you'll get the first order variation of a right-handed spinner. You'll get an I theta I minus, sorry, typo in my notes here, plus beta I here, instead of a minus beta I. Okay. So there's typically a notation that we use to distinguish right-handed and left-handed spinners. So this notation is not going to be so important this semester, but it'll be more important next semester when we talk about the standard model. So the notation that we'll use that a left-handed spinner is given by an index that runs from 1 up to 2. That'll be a Roman letter, A, B, C, H, so forth. And to describe a right-handed spinner, we'll use an index with a dot on it. Okay. So these are sometimes referred to as dotted or undotted indices, the bane of many a doer of quantum field theory problem set. But don't worry, you won't have to deal with them this semester. Okay. But this dotted versus undotted index notation is useful because it helps us distinguish clearly between right-handed spinners and left-handed spinners. And often, the handedness of a spinner is referred to as the chirality of a spinner. So why is this called chirality? Why is this called handedness? Well, the important thing to note is that if you do a parity transformation that takes x to minus x, takes all the spatial directions to minus the spatial directions, then this parity operation, well, the angular momentum operator, J, is unchanged under parity because it's x times p, and x and p both pick up a minus sign. But the generator of boosts is an x times time, and x times time picks up a minus sign because time is unchanged under spatial parity. Okay. So this is under xi goes to minus xi. Okay? And so this interchanges the ends and the end daggers. And so under parity, right-handed spinners and left-handed spinners are interchanged. Just like your right hand and your left hand are interchanged under parity, right? If you take your, if you're right-handed, then in a mirror, you look in a mirror, it looks like you're left-handed, right? So that's why we call these handedness. Okay. So just as an exercise, who can tell me how these spinners will transform under time reversal? I mean, there are two possible options. You have a 50-50 chance. How many people think that they will be interchanged under time reversal? 2. How many people think they will not? Okay. 50%, 50-50, so that's about right. So under time reversal, J goes to minus J, right? And K goes to minus K. And so N and N dagger are not interchanged. Okay? They just go to minus themselves. So right-handed and left-handed spinners are not interchanged under time reversal. Okay. Good. Okay. So having introduced these spinners, how can we construct some sort of interesting dynamics for the theory? Well, to construct dynamics, we need to construct an action. And an action is a Lorentz invariant scalar. So what sort of scalars can we construct out of these spinners? So the first thing that you might try is the following. Okay. So let's consider, say, a right-handed spinner. Okay. So this is a two-component object, and a scalar is something with no components. And the first thing you might try and do is write down psi dagger psi. Okay. So let's see what happens when we take psi dagger psi and we do a Lorentz transformation. Okay. So just to remind you, under a Lorentz transformation, a right-handed spinner picks up I theta I minus beta, no, plus, sorry, that was a typo in my notes, plus beta I times sigma I psi right. So if you take the adjoint of that equation, you'll get psi right dagger. You can use the fact that the Pauli matrices are all Hermitian, sigma dagger is equal to sigma, and you'll get 1/2 times minus I theta I plus beta I times sigma I. Okay. Since the Pauli matrices are Hermitian. If you don't remember that fact, you should verify that for yourselves. Okay, so what happens when you take this putative scalar quantity psi dagger psi? Well, that's the variation of psi right dagger times psi right plus psi right dagger times the variation of psi right. So we just plug in these formulas over here. And what do you get? Well, if you stare at that for a second, you'll see that the theta terms cancel, but the beta terms do not. So what you get is psi right dagger sigma. Here, let me write it like this. What you get is beta I times psi right dagger sigma I times psi right. Okay, well, this quantity has many wonderful features, but being 0 is not one of them. So that means that psi dagger psi is not a scalar. Okay. But we've discovered this other new interesting quantity right here. Now, what is this quantity? Well, this is actually a set of 3 quantities, and it looks a little bit like a vector. Looks a little bit like a 3 vector. So let's ask how that guy transforms under a Lorentz transformation. Okay. So the variation of psi right dagger, sigma I psi right, under a Lorentz transformation. So this is a little more work because we'll have to multiply out some Pauli matrices. So we get the sum of 2 terms. So first, let's vary psi right dagger. So you get a 1/2 times psi right dagger times minus I theta I plus beta I. Sorry, I should call that index j. Sigma j times sigma I psi right plus 1/2 psi right dagger times sigma I times I theta j plus, here, let me write this as sigma j times I theta j plus beta j times psi right. So I can then write this as the sum of 2 terms. So first of all, what I want to do is use the multiplication rule for the Pauli matrices. So remember that Pauli matrices, so their commutator is equal to another Pauli matrix, and their anti-commutator is equal to 1, okay, delta ij, meaning they all square, they anti-commute with one another, and they square to 1. So you can summarize that by this multiplication rule for the Pauli matrices. Remember, if you ever forget the multiplication rule for the Pauli matrices, just remember it's the same as the quaternions. That's a joke. Okay. Anyway, if anyone ever tries to confuse you by telling you what a quaternion, telling you about quaternions, they're just Pauli matrices. Okay. My jokes are really falling flat here. Okay. So we can go ahead and just plug that in here. What do you get? Well, you get really a sum of two terms. So you'll get beta I times psi right dagger psi right. That's the term where we use sigma I, sigma j is equal to a delta ij. So in that term, the thetas cancel because of this minus sign there, but the betas do not. And then we get a second term involving the thetas. So you get a theta j epsilon I j k psi right dagger sigma k psi right. Okay. So let's take a look at this equation for a second. So at first sight, this doesn't look very encouraging. But let's think about first the case where all the betas are equal to 0. Let's just consider a rotation. So the betas are equal to 0. Then what is this quantity here? Well, this quantity looks like a 3 vector. And what is this transformation rule? Well, this is the transformation rule for a 3 vector under a rotation by an angle theta about the axis xi. So in fact, that theta term is very natural here. It says that this quantity, psi dagger sigma I psi, looks like a 3 vector under a rotation. Now what about a boost? Under a boost, it looks like this quantity psi dagger sigma I psi is transforming by this boost parameter into psi dagger psi. And likewise, we saw that under a boost, psi dagger psi transformed into psi dagger sigma I psi. That's exactly what a 4 vector is supposed to do. Under a boost, the 0 component of a 4 vector transforms into the other 3 components, and the 3 components transform back into the 0 component. And under a rotation, the 0 component of a 4 vector is invariant, and the other 3 components mix, just as they do for a normal rotation. So what that means is that psi right dagger, the 4 vector, whose components are psi right dagger psi and psi right dagger sigma I times psi right. So this is a 4 vector under Lorentz transformations. The fact that that sigma has an I index is not an accident. An I index is a vector index. And so that sigma I is transforming under rotations just like a 3 vector. To make this notation a little bit simpler, what we can do is define a 4 vector, sigma mu. This is a 4 vector, each of whose components is a 2 by 2 matrix. The first component is the identity 2 by 2 matrix, and the other are the 3 Pauli matrices. And then the statement that we've proven is that psi dagger sigma mu psi is a 4 vector. So that mu index is really a 4 vector index. Transforms under a Lorentz transformation just like a 4 vector. And similarly, if we were to consider left-handed spinners instead of right-handed spinners, then we would need to define something that I'll call sigma bar, which is a vector of 2 by 2 matrices that differs only by a sign, and psi left dagger sigma bar mu psi left is going to be a 4 vector. Okay, so my initial goal was to try and construct a scalar. I failed in that goal, but I did manage to construct a vector. And if you think about it, given this, it's now very easy to go ahead and construct a scalar. Why? Because there's another way I know of constructing vectors, and that's by taking something and taking its derivative. You take any function of space-time, you take its derivative with respect to x mu, and then that transforms like a vector under Lorentz transformations. So in particular, psi right dagger sigma mu d by dx mu psi right is a scalar. This is the simplest scalar that you can construct from psi. One of the interesting points to note, and a very important point to note, is that there are no scalars that we can construct from psi from one of these chiral spinners without taking derivatives. The simplest scalar you construct involves one derivative. Of course, there are more complicated scalars that you could construct that would involve more derivatives. Okay. But that means that if you wanted to describe the dynamics of one of these spinor fields, then you would start with an action which would be proportional to psi right dagger sigma mu d by dx mu psi right, and this would be a good action to try and define a set of equations of motion for these spinors. Now, there's one final subtlety, which is that we like our actions to be real. Okay? These spinors psi are not necessarily real. I've at least not so far defined them to be such. Those Pauli matrices sigma are certainly not real. And it turns out, as is sort of easy to see, that if you want your action to be real, you need to put a factor of I there. Okay. To see this, so this I is to keep the action real. And to see this, well, let's just take the complex conjugate of this quantity. So what is that? Well, that's equal to d by d x mu of psi right dagger times sigma mu dagger, which is otherwise known as sigma mu, because sigma mu is Hermitian, times psi right. And then you can integrate by parts to write this as psi right dagger, sigma mu d by dx mu, psi right, plus the total derivative. And you get a minus sign here because you have one derivative that you're integrating by parts. So that means that if you want a real action, then you need that I up front. So an interesting thing is happening here, which is that unlike for a scalar field where our action was quadratic in derivatives, for a spinor, the natural action and the natural kinetic term is linear in derivatives. And so this is the kinetic term for a right-handed spinor. And there's one interesting thing to note here, very interesting thing to note, which is that because there are no scalars that you can construct from psi without taking derivatives, no mass terms are possible. Or at least there are no mass terms that are possible involving just psi right. Okay. As we'll see in a few minutes, if you have both a psi right and a psi left, it is going to be possible to construct a scalar quantity in the Lagrangian without taking derivatives. That'll be something we would interpret as a mass term. But just for the two-component chiral spinor, it's impossible to write a mass term. This is a wonderfully important fact which is useful to explain all kinds of physics. So this is the action. What are the equations of motion? The equations of motion which follow from this action are just found by doing the usual variational principle. So, just as for a complex scalar field, you can write down the equations of motion by regarding phi and phi bar as independent degrees of freedom and varying them both separately. For a spinor, you can think of psi and its complex conjugate or its adjoint as independent degrees of freedom and find the equations of motion by varying them separately. And so you can see that just by setting the variation with respect to psi dagger equals to 0, you get this equation of motion. Okay. So it's a linear equation of motion rather than a quadratic equation of motion. It's linear in derivatives instead of quadratic because unlike for a scalar field, for example, we can actually, or a vector field for that matter, we can actually construct a Lorentz invariant kinetic term that's a scalar involving only one derivative. And similarly, for a left-handed spinor, the Lagrangian psi left dagger sigma bar mu d by dx mu psi left is invariant, and the equations of motion are sigma bar d by dx mu psi left is equal to 0. Okay. Any questions before I continue? Yes. From the equations of motion, you cannot say that d mu psi is 0. Right. So this is an equation of motion for this is two equations for two unknowns. Psi is a two-component object. Psi right, say, is a two-component object. And this is two equations. The mu indices are contracted. Right? So this is two equations for two unknowns. Just like for a scalar field, a real scalar field, you get one equation for one unknown. Or for Maxwell's equations, d mu, f mu nu is four equations for the four components a mu of the vector field. It's two equations for two unknowns. That means that in general, there'll be a finite number of solutions. And in fact, we'll write down the solutions. In fact, we wrote down the solutions the first week of class. Okay? Although it wasn't immediately apparent, we were using a slightly different notation. Good. Other questions? Okay. So these chiral spinors are interesting and they're very important, but they don't allow for mass terms. Okay. So in particular, these describe particles without mass. Okay. a mass term would be some sort of term that we could add to the Lagrangian that would be a scalar that has no derivatives in it. And we saw that if you just have a psi right, you can't do that. But let's imagine that we have a psi right and a psi left. And then let's imagine writing down a term that looks like psi left dagger psi right. So what is this? Well, the variation. So that's going to be the variation of psi left dagger psi right plus psi left dagger times the variation of psi right. So what's the variation of psi left dagger? Well, let's go up here and look for the variation of psi left. So the variation of psi left is 1/2 I theta I minus beta I sigma I psi left. So the variation of psi left dagger is going to be psi left dagger, and then a Pauli matrix, because the Pauli matrix is Hermitian, and then 1/2 minus I theta I minus beta I. So let's just copy that, remember that, and copy that down here. So we get a psi left dagger, and then a sigma I, and a 1/2 minus I theta I minus beta I times psi right dagger, and then plus psi left dagger times the variation of psi right, which is I sigma I times 1/2 I theta I plus beta I psi right. And you see that everything cancels. So to describe particles with mass, what we need is both a psi left and a psi right. So you need a right-handed and a left-handed spinner. And the Lagrangian that describes a particle with mass will be the kinetic terms that I wrote down above for psi left and psi right, along with this coupling term that is psi left dagger times psi right. And again, to make the action real, we better add in the complex conjugate of that. And this is the action that describes a spin 1/2 particle with mass. In particular, this is the action that will describe, for example, an electron. So, in fact, there is a way of making the this action and the resulting equations of motion look considerably simpler. So in particular, rather than considering two component spinners, we could consider one 4-component object. So I'll just call this psi without an R or an L. This will be a 4-component object whose first 2 components will be the left-handed spinner, and next 2 components will be the right-handed spinner. I will then define psi bar not to be the adjoint of this 4-component object, but rather to be the adjoint with the order of the rights and lefts reversed. So this is not psi dagger. And I will then define a set of four matrices known as the gamma matrices, which will be 4 by 4 matrices, which are off diagonal, and whose components, so gamma 0 is 0, 1, 1, 0, and gamma I is 0, sigma I minus sigma I 0. These are a set of 4 by 4 matrices, written here in block 2 by 2 form. And then with this notation, the Lagrangian is psi bar I gamma mu d by dx mu minus m times psi. So let's go ahead and just check that. Let's just stare at it for a minute and convince ourselves that this Lagrangian that I've written down is identical to the Lagrangian that I've written above up here. So first, let's just look at this mass term here. You can see that my definition of psi bar involved switching psi right and psi left here. Okay. That was necessary in order to make the psi lefts and the psi rights meet up in the right way here. And you can see, likewise, that because of that, I had to make this gamma mu off diagonal, okay, so that I get a psi right times a psi right here, and this sigma here is that sigma here, and this sigma bar is that sigma bar here. Okay. So this 4-component spinner is known as a Dirac spinner, and it's constructed out of a pair of chiral spinners, typically referred to as Weil spinners or Weil spinners, and for the remainder of the semester, it's really going to be the Dirac spinners that are going to interest us the most. Okay. So, in particular, it turns out that an electron is a Dirac spinner, or at least in quantum electrodynamics, we can describe an electron as a Dirac spinner. But later on in this course, when we consider the standard model of particle physics, we'll find it necessary to describe the basic particles in terms of Weil spinners rather than just Dirac spinners. In particular, in quantum electrodynamics, everything will be formulated in terms of Dirac spinners. And in particular, the Dirac spinners are parity invariant, as maybe you'll check on a future problem set. This Dirac Lagrangian is parity invariant. But we saw above that Weil spinners are not parity invariant. They get interchanged under parity. And it will turn out that in the standard model, as formulated in terms of Weil spinners, the theory is not going to be parity invariant. This is one of the signature features of the standard model of particle physics. It's not parity invariant. Scattering amplitudes, cross-sections depend on the handedness of the particles that you scatter. Likewise, it'll turn out that the standard model is also not time reversal invariant or charge conjugation invariant. It will only be invariant under the full combination C, P, and T, all performed simultaneously. Okay, so it's straightforward now to write down the equations of motion coming from the Dirac Lagrangian. So again, the easiest way to do this is to regard psi and psi bar as independent fields, and you get one equation from varying psi and another from varying psi bar, and the equation that you get by varying psi bar is just this one, and this is precisely the Dirac equation that we met in the very first week of class, when we naively tried to take the square root of the relativistic Schrodinger equation. Okay. So exercise, check that this is the Dirac equation that we encountered earlier. In particular, what you should find is that the matrix that I called gamma 0, so 0, 1, 1, 0, is the thing that we called beta when we studied the Dirac equation earlier, and the gamma i's are the things that we called alpha. And you probably even verified in a problem set the relationship between these gamma matrices and the alpha and beta matrices. Okay, so starting next class, what I'm going to do is give a more thorough derivation, or a more thorough discussion of the Dirac equation, its solutions, and how we will go about coupling the Dirac equation to electromagnetism. And hopefully we'll end next class with the full glory of quantum electrodynamics. Okay. And then starting next week, we'll begin thinking about how we actually do computations in quantum electrodynamics. Okay. So maybe I should stop here, though, unless there are any other questions. Good. Okay, see you Thursday.